Think about this for a second. How does a self-driving car dodge a pedestrian who suddenly steps off the curb? Or how does a delivery drone swerve around a flock of birds that it never saw coming? This is one of the biggest challenges in robotics today, teaching machines to navigate a world that's constantly and unpredictably in motion. So, how on earth do they do it? Let's dive in.
Here's what we're going to cover. First, we'll nail down the core problem and look at one of the first big ideas for solving it. Then, we'll see where that idea kind of falls apart, explore the modern toolkit of solutions, and finally, check out how these incredible technologies are being used out in the real world right now.
All right, so the first thing you have to understand is that for a robot, the problem isn't just about following a map. Not at all. It's about dealing with everything that the map doesn't show.
I mean, a pre-planned route is totally useless the moment something unexpected, a bird, a ball, another robot, crosses its path. And that, right there, is the heart of the problem.
Yeah, in robotics, they have a fancy term for this, a dynamically uncertain environment. It's really just a way of saying the world doesn't stand still. And building systems that can adapt to this constant change, well, that's the ultimate goal.
So, how did engineers first even try to solve this? They came up with a surprisingly elegant and clever concept. What if we could navigate with invisible forces? It's called the Artificial Potential Field, or APF for short. The best way to picture it is to imagine placing a powerful magnet at the robot's final destination, pulling it forward. Now imagine every single obstacle is also a magnet, but one that's pushing the robot away. The robot just follows the path created by all these invisible forces.
So you've got this attractive force pulling the robot to its goal, and then a repulsive force pushing it away from anything it might crash into. The robot's path is basically just the sum of all these pushes and pulls. Seems super simple, right? But, and this is a big but, there are some pretty critical flaws.
As brilliant as that whole artificial potential field idea sounds, it has a couple of major and sometimes completely paralyzing flaws. So here's the first big trap. It's known as a local minimum. Imagine a robot trying to go through a doorway. The repulsive force from the left side of the frame is pushing it to the right, and the force from the right side is pushing it to the left. If those two forces are equal, the robot just gets stuck. It's totally paralyzed between them, unable to move forward at all.
And this isn't just some small theoretical issue. A huge amount of modern research is dedicated specifically to solving this exact problem, getting robots unstuck from dead ends and narrow paths. It's a real-world roadblock for robotics, for sure.
The other big headache is when an obstacle is sitting right next to the goal. The obstacle's push can be so strong that it completely overpowers the goal's pull. So the robot gets close, but it can never actually reach its target because that repulsive force is just way too powerful.
Okay, so the basic idea has some holes. How do we fix it? Well, researchers have developed a whole toolkit of really sophisticated strategies to get around the weaknesses of that basic APF method.
And we're not talking about just one solution. It's a whole suite of tools. For example, fuzzy logic control allows a robot to make decisions that aren't just black and white, but based on degrees of risk, like slow down a little instead of just stop. Then there's the velocity obstacle method, which is just brilliant. It calculates a cone of all the possible future positions for a moving object, and just makes sure the robot's own path never crosses it. It's a whole new level of smart navigation.
I love this one though. The obstacle detection and avoidance algorithm, it's described as simulating how a human walks in a totally dark room. You put your hands out, you feel for obstacles, and you adjust your path as you go. It's an incredibly intuitive way to think about how a robot can navigate a space it doesn't have a perfect map of. Okay, so let's take all this theory and see how this advanced toolkit is being put to work to solve some really complex problems out in the real world.
Let's start with high-speed drones. They need to react instantly, right? Well, these systems allow them to avoid not just physical objects, but also dynamic no-fly zones that can pop up anywhere, like an area around an emergency incident. This is what lets them become reliable tools for everything from urgent delivery to disaster response. Or let's scale this up, way up, to autonomous ships. They use these exact principles to navigate crowded shipping lanes, where every other massive vessel is a moving obstacle. This stuff doesn't just prevent collisions, it actually optimizes routes, saves fuel, and makes global trade safer and more efficient. And what about underwater? Down there, the obstacles aren't always solid things you can see. For exploration drones, a dynamic obstacle might be an unpredictable ocean current or a sudden, dangerous change in water pressure. These algorithms help them navigate these invisible dangers, opening up the deepest parts of our oceans for discovery. And of course, it all comes back to driving. This technology is absolutely crucial for self-driving cars. It's about so much more than just seeing other cars. It's about predicting what they might do and assessing risk in real time. This is the core tech that promises to make our roads dramatically safer for everyone.
So we've moved from these simple, almost magnetic push and pull ideas to a seriously sophisticated toolkit that allows robots to navigate our dynamic world with incredible skill. And that really leaves us with a fascinating final question to think about. As these machines get better and better at avoiding us, how do we get better at living with them?